What happens when a species outgrows its cradle and looks to a desolate, frozen rock with the audacious intent of waking it from a billion-year slumber? Imagine staring across the cosmic void at a dead world, a rust-colored desert suspended in the freezing vacuum of space, and deciding to breathe life into its barren dust. This is not a question of mere exploration, but of absolute transformation, challenging the very limits of human ingenuity and our place in the universe. Terraforming Mars represents the ultimate test of our technological adolescence. The concept of planetary engineering involves deliberately modifying a planet's climate, surface topography, and ecology to be similar to the biosphere of Earth. It is a staggering ambition that forces us to redefine what it means to be a spacefaring civilization, demanding a mastery over nature that borders on the divine. The current reality of the red planet is profoundly hostile. The Martian atmosphere is incredibly thin, possessing less than 1% the density of Earth's own protective blanket. It is composed almost entirely of carbon dioxide, offering zero breathable oxygen and virtually no insulation against the plunging temperatures that routinely drop to negative 153 degrees Celsius during the long, dark winters. Unpacking the sheer scale of this deficit reveals why building a habitable environment is incredibly hard. The biggest initial hurdle is the total absence of liquid water on the surface and the lack of a sufficient atmospheric pressure to keep it from boiling away into the void. If we are to try to coax life from this frozen stone, we must first build a sky from the ground up, a task that defies conventional industrial capabilities. One of the most audacious proposed solutions involves the deployment of vast orbital mirrors. These colossal, ultra-thin reflective sails, spanning hundreds of kilometers across, would be positioned in space to catch and redirect concentrated sunlight down onto the Martian poles. The intense, focused heat would sublimate the massive reserves of frozen carbon dioxide locked in the polar ice caps, releasing vast plumes of gas into the thin air. As this sublimated gas floods the sky, a deliberate runaway greenhouse effect would theoretically take hold. The thickening atmosphere would trap more solar radiation, steadily raising the global temperature and allowing the planet's dormant reservoirs of subterranean ice to melt. For the first time in billions of years, rivers of liquid water could carve their way through the ancient, dusty canyons, fundamentally altering the planet's thermal dynamics. Yet this newfound atmospheric thickness introduces another monumental vulnerability. Mars lacks a global magnetic field, possessing only weak, localized crustal magnetism. Without a protective shield, the relentless barrage of high-energy particles from the solar wind would slowly but inexorably strip away the newly engineered atmosphere, undoing centuries of painstakingly slow progress and leaving the planet barren once again. To counteract this cosmic erosion, researchers have theorized the necessity of artificial magnetic field generation. By positioning a powerful magnetic dipole satellite at the Mars L1 Lagrange point, a stable gravitational pocket between the Sun and the planet, we could cast a massive protective magnetic tail over the entire globe. This invisible shield would deflect the solar wind, securing the fragile new sky and allowing the atmospheric pressure to stabilize. Powering such a monumental deflector shield introduces a staggering energy requirement. The magnetic generator would demand continuous, immense power output, far beyond the capabilities of contemporary solar or fission technologies. It necessitates the perfection of commercial fusion energy, a technology that replicates the nuclear processes of the Sun to provide virtually limitless, clean power to sustain the planetary defense system indefinitely. The realization of these interconnected systems shifts our understanding of space colonization from a rapid conquest to a multi-generational human endeavor. The timescales required to thicken the atmosphere, melt the ice, and stabilize the climate stretch across centuries, perhaps millennia. It requires a societal commitment that outlasts nations, demanding a unified, enduring vision for the future of our species that transcends individual lifetimes. Executing a project of this magnitude across such vast spans of time will rely heavily on advanced computational oversight. we will require the deployment of artificial general intelligence, defined as highly autonomous systems that possess the ability to understand, learn, and apply knowledge across a wide range of tasks at or above human level. These digital minds would oversee the intricate, centuries-long orchestration of climate modeling, resource extraction, and robotic labor. The physical labor of terraforming would be carried out by self-replicating robotic swarms directed by this overarching intelligence. These autonomous machines must mine asteroids for the rare metals needed to construct the orbital mirrors and fusion reactors, operating tirelessly in the lethal radiation of deep space without direct human intervention. Maintaining the integrity and purpose of these robotic fleets over centuries is a profound engineering puzzle in itself. Once the physical environment is stabilized, the biological phase of planetary engineering begins through the application of synthetic biology. Scientists would deploy genetically engineered extremophiles, specialized microorganisms artificially designed in laboratories to thrive in extreme radiation and toxic soils. These microscopic pioneers would be tasked with consuming the iron-rich Martian regolith and slowly excreting breathable oxygen, acting as the vanguard of a new biosphere. Over generations, these microscopic architects would transform the toxic dirt into fertile soil, paving the way for genetically modified lichens, mosses, and eventually sprawling forests of cold-resistant trees. The red planet would slowly transition into a vibrant, living green, engineered from the molecular level up to support complex ecosystems and eventually human agriculture. However, this godlike power to reshape a world casts deep ethical shadows. If we discover even microbial subterranean life native to Mars, our terraforming efforts would almost certainly drive it to extinction. The moral implications of annihilating a unique alien biosphere to create a secondary habitat for humanity present a profoundly unresolved philosophical crisis that scientists and ethicists are only just beginning to navigate. We are forced to confront the fundamental nature of our expansion into the cosmos. Do we have the inherent right to overwrite the natural history of another celestial body? This debate transitions humanity from a species of explorers, leaving temporary footprints in the dust, to a species of creators, actively dictating the evolutionary trajectory of entirely new worlds and playing architect with the cosmos. As the centuries pass, the humans who eventually settle beneath this engineered sky will inevitably diverge from their earthly ancestors. The lower gravity, the synthetic biosphere, and the unique cultural identity forged by the terraforming legacy will shape a new branch of human civilization. They will be Martians, living monuments to humanity's greatest triumph of engineering, physically and culturally distinct from the world that birthed them. The quest to build a second Earth forces us to look inward as much as we look out into the vastness of space. When we finally stand on the shores of a newly filled Martian ocean, breathing air manufactured by our own ingenuity, we will have conquered the stars. But the lingering question remains: in transforming a dead world into a living paradise, what fundamental part of our own humanity will we have permanently altered?